Welcome, calculus students, to this video lesson on sample AP questions involving differential equations. In this video, we're going to look at 3 different FRQs from 3 different AP test years that all involved a differential equation of some type. Now, some things to keep in mind is that when you're solving differential equations, you want to always begin by separating the variables. And I want you to note that if you don't separate the variables first at the very beginning, you end up getting 0 points for however many points were allotted for that part of the question. Oftentimes, you can have anywhere from 4 to 6 FRQ points allotted to solving a differential equation, and you get 0 of them if you forget to start by separating the variables. So always begin with that. Then once you've done that and you have all your dependent variables on the left and independent variables on the right, then you can go ahead and prepare both sides for integration, integrating on the left with respect to y and on the right with respect to x, or whatever the independent variables are named. Then when you're finding your antiderivatives, when you're integrating, you want to make sure that at that step you add c. If you forget to add c at that point when you're finding the antiderivatives, then you only end up with half of however many points were allotted, or maybe even less than half, like 2 out of 5 sometimes is all you would get if you fail to add c when finding your antiderivatives. So always remember that part. Then, of course, if you're given an initial condition and asked to find a particular solution, then you would solve for c, figure out what that constant is. But then ultimately your goal is to solve for y. We're trying to find the equation y equals f of x that gave us the given derivative. That's the solution to the differential equation, is the original function y, or the antiderivative. So there's 3 different FRQ types we're going to look at. The first one is a very standard, or what I consider to be a standard differential equation type FRQ. The second one you'll see has a little bit of a twist, and the third one is what I consider to be perhaps the most challenging style of differential equation. What you might also notice, especially in this standard one here, this was from 2016, is that oftentimes differential equations are combined together with slope fields, where you're either asked to sketch a slope field, or sometimes the slope field's provided and you're asked to trace a solution on top of it, things like that. But they do often combine these ideas together. So in this one here, it's asking us to sketch it. So let's go ahead and begin. So they gave us the differential equation dy dx equals y squared over x minus 1. So notice that the derivative is in terms of both x and y. So at these 6 points, each one will have a different slope because the slopes change depending on both x and y. So I recommend making a table of values that has a column for x and for y, and then using those values to find the slope value, which will be found by squaring y and then dividing it by x minus 1. So I notice here I have a column where x is all 0. So I've got 0, 0, 0, 1, 0, 2. That's these 3 ordered pairs here. I then have a second column where the x coordinate is 2 for all those points. So I have a point where x is 2, y is 0, x is 2, y is 1, x is 2, y is 2. So I'm going to plug these into my derivative fraction and get my slopes, and then plot my slopes. So for this point where x and y are both 0, I get 0 squared divided by 0 minus 1, which is just 0. If your slope ends up being 0, then your little mini slope line that you draw will be a horizontal line. It'll look something like that, like a flat dash would indicate a 0 slope. Now here where y is 1, I get y squared divided by negative 1, so that's negative 1, so I'd have a negative slope. Here I have 2 squared divided by negative 1, so I have a slope of negative 4. So what I understand is that that will just be a steeper negative. I don't have to be super accurate about making sure it's going down 4 and over 1. It's all about kind of graphing them relative to each other, so I just know that at the point 0, 2, that slope will have to be steeper negative than the point at 0, 1. Okay, so moving over to this column where x was 2, again I have another point where y is 0. So I can see that anywhere that y is 0, I'm going to have a 0 slope. So I have another flat one again. And then here where y is 1, I have 1 squared divided by 2 minus 1 is just 1. So I get a positive slope there. And then here y is 2, so 2 squared divided by 2 minus 1, I have a steeper positive slope. So now to plot these points, at the point 0, 0, I'm going to just draw a flat little dash there to indicate a 0 slope. At 0, 1, I'll draw a negative slope that's not too steep. And then at 0, 2, I'll draw a negative slope that's a lot steeper. So kind of showing the gaining of steepness as I go up the y-axis. And then at my 2, 0, I have another horizontal slope again. So it looks like maybe there's a horizontal asymptote along where y is 0. And then at 2, 1, I have a slight positive slope, not too steep. And then I have a really steep positive slope at 2, 2. So that would be our slope field for part A. So now moving down to part B, you can see that it's saying, okay, let y equals f of x be the particular solution. So we haven't found the particular solution to this differential equation yet, but we're still going to call it y. And it wants us to find an equation for the line tangent to the graph. So notice it doesn't say find the particular solution, it just says let y represent the particular solution, but instead find the equation for the tangent line. So I want you to put a circle and a star here because this is another concept that is often combined together with differential equations, and that is tangent line approximation. Using a tangent line, tangent to a curve, y equals f of x, that can help us approximate a value for y on that curve. So remember, for finding a tangent line, you just need two things. You need a point at x equals 2, and you need a slope at x equals 2. And then you can use the point slope formula. The point at x equals 2 is f of 2. This is beyond my curve, y equals f of x. The slope at x equals 2 would be my derivative evaluated at 2, right? We have to remember the derivative of a function at a point is the slope of the tangent line at that point. So f of 2 is given right here, that's 3. So that translates to the ordered pair 2, 3, so I can use that for my tangent line equation. Then f prime of 2, that would be what I get when I take my derivative and evaluate it at the point 2, 3. That's what this vertical line means right here. It means evaluate this expression at this ordered pair. So let's do that over here. So f prime of 2 is the value of my derivative, which equals y squared divided by x minus 1 when x is 2 and y is 3. So that would be 9 over 1, which is 9. That's my slope. So I now have my slope to my tangent line. I now have my point to my tangent line, and I just plug it into point slope form. So old school Algebra 1 days, we went like this, y minus y1 equals m times x minus x1. Feel free to use that, right? Then of course we upgraded a little bit in calc. We said, well, y1 is going to be f of x, which in this case is 2, and my slope is going to be f prime of 2, and then x1 is the x value that we're writing the line tangent at, in this case 2. So either way, and then I know in a previous chapter we sort of added the f of 2, or the f of c we called it, to the other side. But what I'm only showing you this here so you can say, so you can see that this formula that was given back when we were learning about tangent lines is really just point slope form. So you're always welcome to kind of revert back to point slope form. So in this scenario, I would have y minus my y coordinate, which is 3, equals 9, that's my slope, times x minus my x coordinate. I will go ahead and add the 3 to the other side, because it's nice to have y alone. But I'm not going to do any more simplifying from there because it's nice to keep this in this version of point slope form. So here is my tangent line, right? This line is tangent to f of x at the point 2, 3. So we can use it to evaluate or approximate points on this function that are close to 2. And so that's exactly what this is asking us to do. It wants us to now find the approximation, the approximate value for f of 2.1. So f of 2.1, so 2.1 is close to 2. Therefore, the line tangent to f at 2 can give us a good idea of what the function at 2.1 is. So this approximately will equal 9 times 2.1 minus 2 plus 3. This right here is a nice reason why we tend to keep things in point slope form, because this will give us just the change in x. So in this case, that's just 0.1, and then that's just 0.9 plus 3 is 3.9. So my y value at 2.1 is approximately 3.9. Now in part C, it's finally saying, okay, find the particular solution. So always make sure you're reading the instruction and doing the right thing at the right time. The last part did not ask for the particular solution. It asked for the tangent line. So I didn't need to find y. Now, however, I am going to need to find y, and it is giving me an initial condition, so I will need to solve for c in the process as well. So let's start by writing it out in its derivative form. So here's our differential equation because it's giving us the equation of a derivative. I am now going to separate my variables, right? We want to make sure we do that first. And remember, when we separate the variables, we can do that with multiplication or division. So these are the only operations that we're allowed to use when separating variables. We cannot separate using addition or subtraction. Okay, so this is a big no-no, right? Cannot separate using addition or subtraction. Must be separable using multiplication or division, which this one is, because I can multiply the dx expression to both sides. I can move it over through multiplication, and I can move the y squared over through division. I can divide y squared from both sides, and that will remove it from the right side, bring it to the left. So then I end up with 1 over y squared times dy on the left, and then 1 over x minus 1 times dx on the right. Remember, since x minus 1 was in the denominator, when I canceled out the y squared, it left a 1 in the numerator. So we keep the x minus 1 in the denominator. So that is step 1. Then I integrate both sides of that, or I prepare both sides for integration. Notice on the left, I'm going to integrate with respect to y, and on the right, I'm going to integrate with respect to x. On the left, it'll be a simple power rule, but maybe first I will rewrite it as y to the power of negative 2. On the right, it's going to require a u substitution, so I will do that one next. Okay, so let's do my power rule on this side. So I'm going to add 1 to the power and divide by that. So I get y to the negative 1 divided by negative 1 plus c, although I'm going to wait to add that c till I get to the other side, but technically I am adding c here, and then I'm combining the constants at the end. But when we do, since we're doing two antiderivatives, we just sort of combine it to the end of the right side. And that's considered to be whatever this constant would have been added to or subtracted to this constant to get just one constant. So we'll think of that as our combined constant. Now for this side, it will require a u substitution. It's because I do have something other than plain x in the denominator here. So I'm going to let u represent x minus 1, the thing in the denominator. And then that means du is equal to 1 times dx. So this will be a very simple one to replace with. So then I get the integral of 1 over u, because I replaced x minus 1 with u, du, because I can just replace dx with du. And the antiderivative for that is the natural log of the absolute value of u plus c. Meanwhile, this can be rewritten as negative 1 over y. Okay, so I've gotten through step 3, but I do need to determine what my constant is, and I also need to solve for y. I think I'll go ahead and solve for c right now using the point 2, 3, right? That was our initial condition given at the start of this problem. So I'm going to plug in 3 for y. Oh, and I need to sub my x back in. Almost forgot there. So I have ln of 2 minus 1. Let me just write it in terms of x first. So we sub our expression for u back in, because this is an x value, right? Not a u value. So then I get negative 1 over 3. is equal to the natural log of the absolute value of 2 minus 1 plus c. So that's negative 1/3 equals natural log of 1. But the natural log of 1 is 0. So my constant is equal to negative 1/3. So here's what I have so far, because I have to take that and plug it back into my equation. So now I know that negative 1 over y is equal to the natural log of the absolute value of x minus 1 minus 1/3. But I need to solve for y. So the first thing I'm going to do is get rid of this negative in front. I cannot have anything in front of my y, so I'm going to multiply everything by negative 1, right? Both sides of the equation will get multiplied by negative 1. And that'll cancel that out. So then I will get closer to isolating y. So now I have 1 over y is equal to negative ln plus 1/3. So we can sort of reverse the order of the subtraction. So it's positive 1/3 minus the natural log of the absolute value of x minus 1. Okay, so now I notice that this is the reciprocal of y. And if I want to find y, I'm going to take the reciprocal of this side. But I think what I might do first is get a common denominator to make this one fraction and make it easy to flip. So I'm going to multiply by my ln expression by 3 over 3. So then I get this. 1 over y is equal to 1 over 3 minus 3 times the natural log of the absolute value of x minus 1 over 3, which then allows me to combine those numerators together. And then I will take the reciprocal. So if you can, I want you to follow me over here. So I'm going to say that since the reciprocal of y equals 1 minus 3 natural log x minus 1 over 3, then y would be the reciprocal. I'm basically going to flip both sides. So y over 1, in a sense, is equal to 3 divided by 1 minus 3 natural log of x minus 1. So now that I have y by itself, nothing in front of it, it's not in the denominator anymore, then that is my particular solution. That is the function that if I took its derivative would equal this squared divided by x minus 1. So now what I want to show you is what the scoring guidelines look like for this question. So this was the scoring guidelines put out by College Board to show what and how you get points for this question. So part A, that was back when we were making our slope field, and you can see our slopes looked basically like these here. Steeper slopes at the top, not as steep in the middle, and then flat on the x-axis. So you got 2 points for part A. And by the way, the FRQs on a traditional AP test are always out of 9 points. So 2 of those 9 points went just to making the slope field. 1 for the slopes that were both 0, and 1 for the slopes that were, positive or negative. Then for part B, they allocated 2 more points. 1 for getting the tangent line equation right here, which you can see is what we had as well. You can see that they also left it in point slope form, or this version of it, which you're also welcome to do. And then 1 for the approximation for f of 2.1. So 1 point for each of those. For part C, they gave a whopping 5 points. And this is pretty common for when you're asked to solve a differential equation. Lots of opportunity for partial credit here as long as you separate the variables first. Note that you get 0 of the points. It does not matter if your answer eventually matches this. You get 0 points if you don't start by separating the variables. So you can see they started here by doing that. They took the antiderivatives of both sides, and then you have to add your constant of integration when you're taking your antiderivatives. It's okay to add just a single constant on the right side because we can consider that a combined constant. But note that if you didn't add that right there, you would only get 3 out of the 5 points. So you could still get 1 point for separating the variables, 1 point for each antiderivative, so they allocated that here. So 1 point for this, 1 point for that, but then that's it. If you didn't add C right then, you wouldn't be able to get the last 2 points. So then they gave a point for basically adding C and then solving for C, getting the negative 1/3. And then the last point was getting Y alone. Now you might notice here they just literally flipped it over. They didn't bother getting a common denominator, which I guess is okay. They just took the reciprocal of y, and then that was their final answer. So now let's take a look at question 2. So this one was actually from the year before, from 2015, question 4. So in this one, I say it's a slight twist because they're giving us a differential equation, but they're not going to ever actually ask us to solve for the particular solution because there's no way to separate these variables using only multiplication or division. But they will still have you make a slope field for it and ask you other questions about it. So that could happen on this year's test as well. So again, we're going to go ahead and make a slope field for these 6 points. So I start by making a table of values for my x, my y, and my dy dx. So in this case, again, I have a column where x's are 0, and then my y has values of -1, 1, and 2. And then another column where x is 1. And again, I just need to do 2 times the x coordinate minus the y coordinate to determine my slopes at each of those points. So here I get +1, that's a positive slope. And then this slope here will be negative. And then at this point here, I will have a steeper negative, right? So when we have multiple positive or negative slopes, we just sort of graph them in relation to each other, relative to each other. And then here, where my x values are 1, this one becomes 3, right? So that would be a steeper positive. This is another slope of 1 again, and a slope of 0. So we'll have 1 horizontal slope in this one. So then I just come over to the graph and plot my slope. So at 0, -1 right here, I'd have a positive slope that's not the steepest slope. And then as I move up to this point, it's now negative. And then as I move up to this point, it's a little bit more negative. So still facing down, but a little bit steeper in relation to the slope of -1. Then when I move over to 1, -1, I have a steeper positive. So a slope of 3 is going to be steeper than the slope of 1. And then up here at this point 1, 1, I'm going to have a slope that's like parallel to that one, about the same steepness, right? Because they're relative to each other. And then a flat slope here. So positive, negative, steeper positive, regular positive, and flat. So now in part B, instead of asking us to go backward and find y equals f of x, they're asking us to find the second derivative. So sometimes that's what they'll combine together with slope field questions, is they'll combine this idea of implicit differentiation and comparing different rates of change. So they want us to find the second derivative and then determine the concavity of all the solution curves. Now remember, the solution curves are the y equal f of x curves. So we're going to have to use the second derivative to determine the concavity of the solution curves, which is the original function, in quad 2, and then we're going to have to give a reason. That means some kind of verbal explanation. Okay, so let's go ahead and find the second derivative. So the second derivative is just the derivative of the derivative. The first derivative of the first derivative. So it's going to equal the derivative of 2x minus y with respect to x. So then for the 2x part, that's just 2. But for the y part, you're taking the derivative of y with respect to x. That's dy dx. Right? Derivative of y is just dy dx. But we know what dy dx is. This whole thing is dy dx. So we can plug it in there. So we get 2 minus the equation or expression for dy dx, which is 2x minus y. Little distribution there gives us 2 minus 2x plus y. That is my second derivative in terms of x and y. That's my d2y over dx squared. And then we need to consider whether or not this is positive or negative, because that's how we determine concavity. It's based off the sign of the second derivative. So we need to look and consider what the signs of x and y are in quad 2. We know in quad 1, x and y's are positive. In quad 2, x is negative and y is positive. So that means if I'm picking a point in quad 2, I'd be plugging in a negative number in for x right here, and then a positive number in for y. That negative number I'd be plugging in for x would cancel with the negative 2 being multiplied to it, and I'd have 2 plus positive number times 2 plus some other positive number. Altogether, that's going to give me a second derivative that's greater than 0. So hopefully you remember what that means in terms of concavity of y. Concavity of y would be up. If the second derivative is positive, y is concave up. So we could say this. The solution curves for the given differential equation in quadrant 2 will be concave up because the second derivative is positive or greater than 0 for all points x, y in quadrant 2. So we determined our answer and then we justified it or gave a reason for it with these words. Now in part C of this question, it's saying, okay, let y equal f of x be the particular solution that goes through the point 2, 3. It doesn't say find it, it just says let it be that. And then it wants to know, does this function have a relative min, a relative max, or neither at x equals 2, and then justify your answer. Again, that requires some type of verbal explanation. Well, to determine whether or not something's a max or min, first we want to see if the derivative equals 0 or undefined, right? If the derivative is 0 or undefined, that's going to locate for us a potential max or min, and then we could check to see if the second derivative is positive or negative. So let's first check the derivative. We're going to evaluate the derivative at the point 2, 3. So the derivative itself was equal to 2x minus y. So at the point 2, 3, that would be 2 times 2 minus 3, which is 1, which is not 0 and is definitely defined. So because the derivative is not 0 or undefined, then this is neither. The function has neither a max or a min at x equals 2. In fact, since the derivative is positive, the function is in the process of increasing. So it has neither a max nor a min. So we could say y equals f of x has neither a max nor a min at x equals 2 because f prime of 2 is not 0. And more specifically, it's not changing signs. Since it's not passing through 0, it's not changing signs. Lastly, in part D, so this one here was a very, very tricky question, and I recall it was one of the more missed questions that particular year. And I just want to show it to you because it's kind of one of those curveballs that AP tests can throw from time to time. So it starts out like this. It's saying, find the values of the constants. So remember, the m and b that we're trying to find are constants. And they basically are the slope and the y-intercept of a linear equation that would be the solution to that differential equation given earlier, the one where dy dx equals 2x minus y. They're saying find a slope and y-intercept for some linear function that could be the solution to this equation. The y equals f of x, that if I took its derivative would equal 2x minus y. So basically you have to just use everything you know about derivatives and solutions to differential equations and really just math in general. But one thing we know is that for a linear equation, the derivative is just the slope. So if y equals mx plus b is the solution, y equals f of x, then the derivative would have to equal m, the slope, right? Derivative is the slope. And then that means that that would be the same thing as what this is, because if this is the solution to this differential equation, then its derivative also equals 2x minus y. So what that means is that this m, which is the slope of this line, therefore its derivative, would equal this equation given for its derivative. Derivative equals derivative. But if the solution is this equation, then I could plug that in for y in the derivative. So I could say that m is equal to 2x minus this mx plus b solution that we were saying is the solution. And I'm trying to find the m and b that would make this true. So just a little bit of kind of rearranging gives me 2x minus mx minus b. And then if I subtracted the m over, I could say 0 equals 2x minus mx minus b minus m. So then I notice I kind of have another linear equation here. In fact, maybe I could factor my x out. I'd have 2 minus m and then minus b minus m. So I can see that this is one constant here, right? Because remember earlier, m is just a constant and b is just a constant. So I could almost think of this being another constant as well. So this is like its own linear equation, right? Some constant times x plus some other constant, and that whole thing is equaling 0. And I want this to be true, by the way, for all values of x and y. I want to make this solution have this same derivative for all values of x and y. So then this has to equal 0. According to what we've found so far, this new linear equation would have to be 0. Well, that could only happen for all x if these two constants were both 0. Because then I'd have 0 times x plus 0. So 2 minus m would have to be 0, and then negative b minus m would have to be 0. And if 2 minus m is 0, that means that m is 2, basically. And so then if m is 2, well, let me continue over here. So then if negative b minus m is 0, then negative b would have to equal m. Or you could say b would have to be like negative m or the opposite of m. So if m is 2, then b would have to be negative 2. Okay, so this is what we're saying. We're saying that if I want my solution to this differential equation to be linear, to be y equals mx plus b, then the slope would have to be 2 and the y-intercept would have to be negative 2. So I'm going to just check that really quick. Is we're saying that y equals 2x minus 2 could be a solution to this differential equation, dy dx, where that equals 2x minus y. So I want to check, could this possibly be a solution to that? Well, in order for this equation to be a solution to this derivative, then its derivative has to equal this. So the derivative of my solution, 2x minus 2, is 2. So the question is, does that equal 2x minus y? If y equals 2x minus 2. So let's find out. 2x minus 2, right? This is the equation I'm saying y equals up here. So if so, I get 2x minus 2x plus 2. And yes, that does in fact equal 2. So this is true. If m is equal to positive 2 and b is equal to negative 2, and I get this solution, y equals 2x minus 2, that does in fact have a derivative, which equals 2, by the way. But it turns out that for every single point on this line, 2x minus 2, if I do 2 times the x value minus the y value, which equals 2x minus 2, I'll get 2 every time. So it is true in this case that the derivative of this function equals 2x minus y. So let's just take a quick peek at the scoring guidelines for this one as well, just so you can get a sense of how the points are allocated. So you can see again, they did give 2 points for the slope field. Again, but this time instead of splitting it up by 0 slope and non-zero slope, they split it up by the 2 columns where x was 0 and 1. And they just kind of check and see if you have the right relationship, right? So these were kind of the same steepness, but that was a little steeper. These were kind of the same steepness, but this one's negative, that one's positive, but then that was a little steeper. So they just kind of look for that and give the points accordingly. They gave, for the one where you had to find the second derivative, they gave 1 point for finding the correct second derivative, and then 1 point if you recognize that it was concave up, but they only give you that point if you also leave a reason. So you have to explain that in quadrant 2, x's are negative, y's are positive, so my second derivative is positive. That's why the solution curves are concave up. If you don't give the reason, then you either get half the point or none of the point. In part C, it gave 1 point for determining the value of the slope. So they know that if you're checking the value of the slope, then you're on the right track. So you get 1 point even just for considering that, trying to find that value, which remember we found was 1, which was not 0. So then you have your conclusion with your justification. So you only get this point if you add in that verbal reason. So because the derivative was not 0, then it's neither a max nor a min. And then in D, they gave 3 points. That one was harder. So the first one they gave is just for finding this. So even if you really weren't sure what the heck to do from there, you still get 1 point for knowing that the derivative of this function is m. You got another point for setting these equal to each other, recognizing that, well, this is the equation given earlier for the derivative, therefore that should equal this slope. You got 1 point if you were able to recognize that. Even if you weren't able to kind of make this leap and get these values, you still got 2 out of the 3 points. So still pretty good. So the point here with FRQs is to go for partial credit. Just put down what you know, as much as what you know, and get as many partial credit points as possible. And even if you can't arrive at the more difficult conclusions, you can still get a decent amount of points for those questions. Last but not least, we're going to take a look at the more difficult type of differential equation. This was from 2017, and I remember this was a very popular theme on Reddit that day, the potato question from the calc. I think it was on both the AB and BC exams. Now, this is probably one of the more difficult ones because the derivative is only in terms of what I call the y value. Of course, it's h here, but that's because that's how they're naming this function. They're naming this function as h of t. So that means h is kind of like y and t is kind of like x. And notice in my derivative, it's only in terms of y. Okay, so for part A, instead of going straight into finding the solution to this differential equation, again, it combined it with this idea of a tangent line. So this is often combined with these differential equations. It just wants us to write an equation for that when t is 0, and then use that equation to approximate the internal temperature at time 3. So we have to utilize this information given earlier in the question. Because remember, to write an equation for a tangent line, we need a point, and in this case at t equals 0, and we need a slope at t equals 0. So the point at t equals 0 is 0, 91, where t was 0 and h was 91. So the slope at t equals 0 will be the value of the derivative at the point 0, 91. So in my derivative, there's nowhere to plug in t, but there is a place to plug in h. So you would have to plug in 91 for h because that's what the internal temperature is at time 0. So that's what you plug into your derivative to figure out what it would be at time 0, and then you subtract 27 and solve. So this then gives me negative 1 over 4 times 64, which gives me negative 16. So that is my slope at the point t equals 0. So for my tangent line, I'm going to do y minus the y coordinate equals my slope times, maybe I'll do t, right? T minus the t coordinate of 0. And then I'm going to add the 91 to the other side. So in this case, I get negative 16t. I don't really need to write the minus 0. And then plus 91. So there's my line that's tangent to, right? This is an approximation for h for values of t that are close to 0. But then what did it want me to do? It wanted me to approximate that internal temperature. That's h, by the way. H is the internal temperature when t is 3. So it wants me to find the approximate value for h of 3, which I can approximate by using this equation and plugging in 3 for t. So negative 16 times 3 plus 91. The internal temperature at time 3 is approximately equal to 43 degrees Celsius. So then moving to part B, you can see they're going to have us find the second derivative, another common theme, right, given these differential equations. And this is going to require us to use skills like implicit differentiation, but then look what they want us to use it for. They want us to use the second derivative to decide if our estimate back in part A is under or over. So we're also going to have to use it to determine the concavity of our solution, h of t, even though we never found the solution. Okay, but let's try to find it first. So the second derivative of h with respect to t would be the first derivative of the first derivative. So let me write what that was so we can remember. So the first derivative of h with respect to t was negative 1/4 times the quantity h minus 27. Again, it was only with respect to h. And look at this, I'm taking the derivative with respect to t. So that's why it's going to require some implicit differentiation. So I'm going to take the derivative of this, basically. That's what the second derivative is. So I'm going to carry the constant. It's going to have the constant of negative 1/4 because it's being multiplied. And then the derivative of h minus 27 would just be dh dt. Because the derivative of h with respect to t is just dh dt, and the derivative of a constant is 0. So then notice you have this expression dh dt in my second derivative. So I'm going to take all of what dh dt equals and plug it in. So this basically appears in its second derivative. So then I'm going to get negative 1/4 times all of this, again negative 1/4, and then the quantity h minus 27. So basically it ends up being 1/16 times the quantity of h minus 27. This is the second derivative of h with respect to t. So that's the first part, finding the second derivative, but then use it to determine whether our answer is an underestimate or an overestimate when we were trying to approximate h of 3. So we need to decide if this is positive or negative at t equals 3. Well, we have to peek back at the wording earlier in this question. Earlier in this question, it said that at time 0, the internal temperature of the potato is 91 degrees. That's H. The 91 degrees is H. And it stays greater than 27 for all times greater than 0. So H remains greater than 27 for all times greater than 0. So let's look at how our derivative is structured here. This value h is going to be greater than 27 for all t greater than 0. That includes t equals 3, right? Because 3 is greater than 0. So if this number is greater than 27, then when I subtract 27 from it, that's going to stay positive. So I can see that my second derivative will be positive for all times greater than 0. So what does that mean about h of t? That means h of t is concave up. That's what that means. And so what does that mean? Well, if you think of it this way, so let's just draw a graph of something that's concave up, right? It could be increasing in concave up or even decreasing in concave up. Either way, if I try to draw a tangent line at some point on a graph that's concave up, the tangent line has no choice but to lie below the curve. It'll always be sort of under the curve if you're comparing the two vertically, right? The line will be below the curve. So this value of 43 degrees Celsius that I got in part A came from the linear equation, the tangent line that was approximating h of t. So h of t is actually a concave up function. This is linear and it's tangent to h of t. So my 43 degrees Celsius would be under. It'd be lower than the true value because it would be on a tangent line that's lying below the curve. So I can say that since the second derivative of h with respect to t is greater than 0 for all t greater than 0, then my approximation for h of 3 in part A must be an underestimate. So moving on to part C, in this part of the question, they gave us an alternative model that could represent the internal temperature. So now they're saying that G represents the internal temperature, and they're giving us this differential equation, which again is only in terms of G, not in terms of T. And they're giving us the same initial condition, that the internal temperature at time 0 is 91 degrees. But this time they are asking us to solve. Find the original function G of T that would give us this derivative, and then use it to find the internal temperature at time 3. Okay, so we're going to start by first setting up the derivative. And then because we're working with two variables, we have to start by separating the variables. That always has to be step 1. But I want to make a little comment here. I'm going to think of this as -1 times this function. And if ever you have like constant multiples, it's ideal. It's not necessary, but it's so much easier to just keep these constants on the right. So I'm going to put keep all constant multiples on the right side of the equation. Now, that's not going to cost you any points if you don't. It's not mandatory. It's just going to save you headache later. So it's just kind of a personal tip. So I'm going to keep the -1 here, but I do need to divide this expression with g minus 27 to the 2/3. Like that whole expression has to go to the other side because I can only separate variables using multiplication or division. So I can't separate the g from the 27. They just it has to all go together. So then that would just leave behind the -1, but I would also need to multiply a dt to both sides to get the dt to the right side. So that would reduce that from here. So then now I have 1 over the quantity g minus 27 to the 2/3 times dg, and then -1 times dt. Now I'll prepare both sides of the equal sign for integration. I'm integrating on the left with respect to g. I'm integrating on the right with respect to t. Now the left side here is going to require a u substitution because I have like more than just plain g plugged into this function. So I'm going to have to let u equal g minus 27. du would just equal dg. Just derivative of g is just dg, and then derivative of 27 is 0. So this will actually be, again, quite a simple u substitution. So we'll rewrite it this way. So it's the integral of 1 over u to the 2/3 du, because I can just swap out dg for du. So it's like really nice u substitution there. On the right side, I can go ahead and just take the antiderivative of -1 with respect to t, would just be -t plus a constant. Here I can use a power rule. I can think of this as u to the -2/3, and I can add 1 to the power and then divide by that. So I would get u to the 1/3 divided by 1/3 plus c, but again we're going to think of whatever this constant was as having been combined with the constant on the right. And then I'm going to replace g minus 27 back in for u. Also, when you divide by 1/3, that's really multiplying by 3. So this is 3 times the quantity g minus 27 to the power of 1/3. And that's all equal to -t plus a constant. Now we were given that initial condition that when t is 0, g is 91. So I can use that to solve for c. So I have 3 times 91 minus 27 to the 1/3 equals 0 plus c. So that's 3 times 64 to the 1/3. Well, 64 to the 1/3 is just 4. And then 3 times 4 is just 12. So my constant is equal to 12. But that's just finding c. I'm being asked to find g of t. So this is what I have right now because I'm going to take that and plug it in here. I have 3 times the quantity g minus 27 to the power of 1/3 equals -t plus 12. First thing I'm going to do is divide everything by 3. So I get g minus 27 to the 1/3 would be -t plus 12 all over 3. Second thing I'm going to do is raise both sides to the power of 3 to sort of undo the cube root. So I'm going to get g minus 27 equals the quantity, maybe I'll write this as 12 minus t over 3 cubed. And then very last thing I'll do is just add the 27. So I get g all the way alone. So now I can say that g of t is equal to the quantity of 12 minus t over 3 cubed plus 27. So that is my equation for g. This equation for g would give me this derivative. The derivative of -1 times g minus 27 to the 2/3. That would be the derivative of this in terms of g. Okay, so that's my solution. That's my g of t. But they also wanted me to use that to find g of 3, the internal temperature of the potato at time 3. So then I just plug that in here. So this would end up equaling 9 over 3, which is 3 to the third, so 27, and then plus again 27. And that gives us 54 degrees. So look at that. Our original estimate was quite under, right? Originally we said 43 degrees, and now after finding the solution and evaluating it, turns out it was actually 54 degrees Celsius at time t equals 3. Let's just take a quick peek at the scoring guidelines for this one as well. So for that first part, when we were finding the equation of the tangent line, it actually gave 3 points because it was, quite tricky. It gave 1 if you found the correct slope. That was challenging, right? Recognizing that you had to plug in 91 for h. And then 1 for finding your tangent line. And then 1 for the approximation of 43 degrees Celsius. So 3 points total for that part. For part B, it was only 1 point for all of that thinking and work. But basically, you had to state the reason to even get that full point. For part C, they gave, again, a full 5 points because whenever you're solving a differential equation, they like to give all these different partial credit points. But again, notice that if you didn't separate the variables at the beginning, you would get none of those partial points. So always start by moving the dt over here and the expressions with g over here. And notice they as well left the -1 on the right just because it's so much easier. And then, of course, we have to remember to add c. If we don't, then we would have only been able to get 2 out of those 5 points, because for this particular one, they only gave 1 for both antiderivatives combined. So probably a half point for getting this one, and then another half point for getting that one. Because we had to then solve for c, so that was worth a point. Then solve for g, getting g alone, that was no easy task. That was worth a point. And then finding our g of 3. Right here, which was 54 degrees Celsius. So that was kind of the point breakdown on that one. So that concludes this video. When we're in class next, we're going to practice some different FRQ questions that all have a similar style. I'll see you there.